Hello, we are Group 5. Our project is APALES, the Automated Parameter Adjusting Laser Engraving System. My name is Nolan. I am a photonic engineer.
My name is Jackson. I'm also a photonic engineer.
My name is Amir. I'm a mechanical engineer.
My name is Ali. I'm a computer engineer.
My name is Kavanash. I'm a computer engineer.
I'm Felipe, and I'm a computer engineer too.
So what is APALES? APALES is a laser engraver equipped with the ability to recognize the material it is engraving. By identifying the material it is engraving, APALES automatically modifies the engraving G-code to match the material's ideal laser power and scan speed. Since each material responds differently to the 450 nanometer laser light, it is essential to modify these parameters prior to the start of an engraving job. Currently, APALES has the ability to differentiate wood, leather, and cardboard to a high degree of accuracy and can modify the same engraving pattern to work perfectly with all three materials. We created APALES with the goal of streamlining the laser engraving process. Currently, no commercial laser engravers are equipped with the capability of detecting the material it is engraving. By adding this ability, APALES saves the engraver user's time by removing the need to manually input ideal laser parameters before each engraving job. Additionally, APALES saves the user money and prevents waste by reducing the frequency of improper engraving jobs due to the wrong laser parameters being input.
Some of our goals and objectives for this project include being able to differentiate between a variety of materials with an 85% accuracy or more, have some material identity prediction within less than 5 seconds, as well as focus on the laser beam to be able to engrave within this specific line width. We also want to create a user-friendly interface that will be able to communicate between the software and the hardware, as well as have a manual control of the Z-axis to be able to adjust it as well.
In order to identify the material that's being engraved, we have incorporated a low-budget spectrometer into our system. In order to identify the material, we collect light from the surface of the engraving material using an LED on the left and a fiber optic cable positioned at roughly a 45-degree angle to capture that reflected light. And then that fiber gets transported to the spectrometer that we've 3D printed. The input of the fiber is here. We have a collimating lens which collects the light from the fiber and directs it towards the diffraction grating, where one mode of that reflected light is captured by this USB webcam, which can then be analyzed by Python on an external computer or laptop.
So this is our laser and focusing system. We elected to use a 450 nanometer 4-watt laser to use a visible wavelength laser so we can actually see the spot size. Our original focusing system had chosen to remove this attached lens on the module and use a 2-lens system of a collimating lens and then the focusing lens to maintain the ideal spot size from the laser diode emitter. But instead, we have now elected to keep this lens on there because of the very high beam divergence from the laser diode, and that is being focused through this 2F system, this single 2F focusing system, and that focuses down to the material, and this height can be adjusted using our manual Z height adjuster.
Hello everyone, this is our final execution for the CNC laser engraving gantry system. As you can see, it perfectly fits in our enclosure, which we intended in the beginning, with the specific size for the base. The base is constructed out of 1020 aluminum extrusions, and these gantry towers are 3D printed, as well as the X-axis tower here. The mounts here are also 3D printed, which of course encompasses the laser lens, as well as the spectroscopy system that has the fiber optics cable as well as the white LED light. Here in the corner, we have our ventilation system, which is just a fan that has an exhaust coming through. This reduces, any toxic fumes that might arise in the enclosure, and it releases them elsewhere. As well as this camera here, this is to monitor the engraver since it is fully enclosed during the engraving portion, so we can keep an eye on the whole entire system.
Good afternoon. I'm going to give you guys a quick overview on the final execution of the PCB design.
So first most here we have the power converter board. So we're going to take in a 12-volt input, and we have multiple JST connectors here from 12, a 5-volt, and then also one for the LED as well, which is also an additional 12-volt. And it's going to be connected here onto our main board, which is going to encompass everything for the drivers, the motors itself, some header pins, and then also the connectors for the laser as well. So here is the input. So as you can see, this light emitting here is just proves that it is being powered correctly throughout the entire system. We have 5 volts being emitted correctly, not just through the power board, but through the entire power, the main board as well. We had some issues with the micro USB that was going to be included into the system. So then we had Dr. Weeks help us in soldering into the exact pins of the USB converter onto a separate USB type A to then plug it into the laptop for the code part. So hardware wise, everything is working, but we had some hurdles in terms of getting that software to run correctly. So as per the suggestion from Dr. Weeks, we have the inclusion here of a CNC controller, which will be able to take in the software specifically for the G-code rasterization.
Hello, this is our APALES app. As you can see here, we can select an option for new material or existing material, and we can choose our COM port selection and our G-code file selection to engrave an image on the material. And you can see on our database, we have brown leather and cardboard already in the database, and we're going to add wood into our database as a new material.
As you can see, this is the new piece of wood that we're going to put into the system right under the spectrometer. And if we close it up, it is being closed in the enclosure so no ambient light gets into our system during scanning.
So we just added wood onto our system. So now we're going to add it in as a new material in our database. So we're going to input the name. Now we're going to add the feed rate, which is the speed at which the laser moves in millimeters per minute. And now we're going to add the S-max G-code parameter, which is the max duty cycle. And this determines like if we need higher S-max or lower depending on the ablation threshold of the material. So let's add that and save it. So as you can see, now it's saved. We can see success. It's in the database. We can see time lapsed 1.874 seconds, and the material array and parameters saved of wood.
So finally, we're going to start an engraving job with an existing material. We set the COM port and the job to be engraved. This is the image preview. So we're going to select existing material to start the spectroscopy. So yeah, the material is captured by the spectroscopy system and classified. And the job is ready to be engraved. So once we click on OK, we can see that the commands, the G-codes, are being sent to our CNC controller, and the job is started. So this is the job that I just sent to the engraver. As we can see, the engraving is going on. This is footage from inside of the enclosure from our monitoring camera. This particular engraving is a vectorized engraving where it reproduces the outline of the image.